Video 1, oxidation numbers. To begin with, let's talk about law of conservation of mass. So the first thing is saying that mass should be conserved. So from reactants to products, you can't just make up mass. You also can't just destroy it. That's the rules. But there's also a law of conservation of charge. The idea is that charge should be conserved in a chemical equation. So with this first example, for instance, iron, there's one iron atom or ion on this side and one over here. So the mass is conserved. Same thing for zinc, 1 and 1. But is the charge conserved? Yes, because if you add up the charges here, 3 plus 0 gives you 3, and on this side 2 plus 1 gives you 3. So mass is conserved in this chemical equation. What about the second one though? Because so often we're like, well, who cares if charge is conserved? But it matters. So the very last equation we're going to balance is this one right here. And it looks balanced at first because you have one aluminum, one zinc, and one zinc. But the charge is not balanced. So therefore this reaction is not considered balanced because the charge is not balanced. So for instance, 0 plus 2 gives you 2. On this side, 3 plus 0 gives you 3. So 2 does not equal 3. This is not balanced. So in order to do this, we should think about first oxidation numbers. With ionic compounds, it's really easy to see, here's the charge on this ion, here's the charge in this one. But if you have a covalent compound, those are not ionic charges. Instead, we give things oxidation numbers, which is just going to tell you the distribution of the electrons inside of that covalent complex. Okay, so that is step 1. So let's look at the rules. Rule number 1 says that if an element is elemental or neutral, then the oxidation state is 0. Meaning, if you see iron, you don't see anything written up here. The oxidation state of this is 0, so it's understood to be 0. Iron, 0. What is the oxidation state of iron? It's 0. Okay? If you see something like this, silver, there's nothing written, no positive or negative written, so it's understood to be 0. That's really obvious, but then when you get to something like this, nitrogen, it's a diatomic molecule, excuse me. So with nitrogen, the rule still stands because the rule says if it's elemental or if it's neutral and there's only one element to it. Okay? Only one element, it's neutral. So what is the oxidation state on each nitrogen? It is 0. Okay, so nitrogen's is 0 in both of these, which kind of makes sense. Because if you got nitrogen that's bound to nitrogen, why would it make sense to make one be plus 1 and one be negative 1 to balance it out? It doesn't. They're both 0. Okay, so that's not true. Both of them are 0. Okay, so if you see anything that's like copper 60, sulfur with multiples on there, they are, each individual atom has an oxidation state of 0. So only one atom, 0. Rule number 2 says that if it's a monoatomic ion, then the oxidation state for that element is the same as the charge. So, same example, you got iron 3+, and it asks you what is the oxidation state of iron? It's 3+. Or Fe2+. What's the oxidation state of this element? 2+. Whatever the number is that's written, that is its oxidation number. Okay? Rule number 3 is for ionic compounds. So what that means, if you have an ionic compound, you look first at the periodic table. And if the periodic table, you look at the nonmetal. Whatever the nonmetal is, assign its charge based on what the periodic table tells you it should be. So oxygen, -2. Chlorine, -1. Then you go to your cation and you give it the charge based on what it has to be to balance out the anion. So for instance, sodium chloride. Chlorine is -1, so sodium has to be +1. Okay? Or potassium oxide. Oxygen is -2, potassium therefore is +1. Uncross those charges, it works the same way. So this is the same thing as figuring out what the charges are of the individual ions inside of an ionic compound, but now we're calling them oxidation numbers. That's the same thing as your charge for an ionic number, okay, or an ionic compound. Okay, so then what about iron 3 oxide? Oxygen is going to be -2, So that means iron has to be positive 3 in order to cancel out. So what that literally means is every iron atom has an oxidation state of plus 3. And every oxygen ion has an oxidation state of negative 2. Alright, rule number 4 is for covalent compounds, which means if it has a fluorine in it, a hydrogen, or an oxygen in it, these guys get to pick their charges first. They're kind of like, dibs, called it. So fluorine always gets to be negative 1, hydrogen gets to be plus 1 for all of our cases, oxygen gets to be negative 2. So you pick those first, and then you assign everything else what they need to be to make it balance out. So meaning, if you got, how about CO2, carbon dioxide, oxygen gets to be negative 2. So what does carbon get to be in order to satisfy the fact that the whole molecule doesn't have any charge, which means it's neutral? So the way you could do this is either A, use logic to try and say, okay, so there's a negative 2 and there's 2 of them, which means oxygen has a total of negative 4, so carbon has to be positive 4. Or you could make a mathematical equation, meaning you have one carbon atom and it's got some charge which is unknown because it gets to be last, plus 2 oxygen atoms times its charge, which is negative 2, and that equals 0 since the whole compound has no charge on it. Now you would solve and you would set that to be x equals positive 4, which is what we figured out just kind of using logic. Okay? And we can do this for more complicated molecules. Okay? So we can do it for more complicated molecules such as sodium hydroxide. So sodium 1 times x plus oxygen, there's 1 of them, times its charge negative 2, plus hydrogen, there's 1 of them, times its charge plus 1. And the whole thing equals 0. Solve for x, and x equals plus 1, which is exactly what you would have guessed based on the periodic table. Using the algebraic equation to solve, I think, is really helpful with big molecules like this, because there's multiple plus 1s, multiple negative 2s, but then I don't know what carbons is quickly just using logic. So in this case, you have 2 atoms of hydrogen times its charge, which is plus 1, plus carbon, and there's 2 of them, times x, because we don't know its charge or its oxidation state, plus 4 oxygen atoms times negative 2, and that whole thing equals 0 because there's no charge up here. So 2 times 2 is 2, plus 2x plus 8, negative 8, equals 0. So negative 6, bring that to the other side, 2x equals 6, and x equals positive 3. Rule number 5 is very similar to the covalent compound rule, except for now you're working with covalent complexes that are charged. Okay, so this can be any kind of charged molecule. What you do is you set up an equation just like you did before, assuming these two are still constant, so fluorine is still negative 1, hydrogen plus 1, and oxygen negative 2, but now you're solving for whatever the other unknown object is or unknown element is in the equation. So in this case, chromium's my unknown, so 2 times x plus 7 oxygens times negative 2. But now what does it equal? It no longer equals 0 because now we have a charge, so it equals whatever the charge is. In this case, negative 2. So then we would solve 2x, this is negative 14, bring it to the other side, equals 12. So x equals plus 6. Which means every chromium atom in this complex has an oxidation state of plus 6. Every oxygen inside of this complex has an oxidation state of negative 2. Okay, let's do another one. Let's do this one. So MnO4 minus. So manganese here is going to be 1 times your x plus 4 times negative 2 equals negative 1. So x equals positive 7. So every manganese has an oxidation state of plus 7. Okay? So what I want you to do, I want you to finish filling in the front side if you haven't done all of those yet. Then try each of the backside. Okay, so some of these are going to be a little easier than others. Some of them, like nitrogen, you need to remind yourself what rule does that apply to. So try every single one of them on the back now.